I welcome you all to the Spark Research YouTube channel. This is Dr. Virchandra, Assistant Professor in the Department of ECE, and here is the another session for this particular course, Analog and Digital Communication. And in this session, we are going to take the contents from this unit third, and this is the second and last part of this particular unit third, right? So we will continue to talk about the baseband and digital modulation techniques. So in this session particularly, we are going to talk about the digital modulation techniques, right? So here we will take the contents related to the matched filter receiver, then probability of error for matched filter, intersymbol interference, and then the I patterns. So here if you like here mostly I have taken the contents from the Bipilati 4th edition. So page number is also mentioned here. If you want, you can follow that book also, right? So further, if you want to prepare for your GATE 2027, you can like these contents will be very helpful for you. And GATE is a very the important exam. Those who are going to complete the BTech. Okay, so here is the syllabus for your third unit. So in this session already we are we have covered the PM, PW and PPM in our recent part along with the digital modulation techniques including the PCM, DPCM and delta modulation also, right? So I will drop the link in the description section. You may go and visit. So in this session we are going to talk about the filter and the ISI related things, right? Okay, so let's go. So first question is that what is this matched filter receiver? So matched filter receiver is a receiver used in the digital communication system. And what is the target? Target is to maximize the SNR, that is signal to noise ratio. And why is this required exactly? Because of the noise, right? So since noise will be added while your digital signal is propagating through the channel, so maybe the noise, maybe the type of the additive white Gaussian noise, that is AWZN. So now question is that how will detect the proper information, right? So that's a difficult to detect. So that is why this matched filter concept arise. So this is important concept to understand in order to detect or demodulate or reconstruct the information from the demodulated masses, right? So a matched filter is a filter whose impulse response is matched to the shape of the transmitted signal. So like whatever the transmitted signal shape you might have, we will try to match it with our filter, right? So that is why this is called the matched filter. So ST is nothing, your impulse response of the matched filter, and ST minus tau is showing the that for the different time what is the transmitted signal, right? So a transmitted signal passes through a noisy channel and receiver applies a matched filter whose impulse response is in the reverse time reverse position of the transmitted signal. Okay, so let's continue. So here is your suppose input signal like PT plus NT. PT is representing the pulse trend, right? NT is representing the noise. So here is your matched filter, that is H of F, H of T in the time domain, right? So now once you will cross, then you will get the P not T and plus minus plus N of T. Further, once you will decode the information, then you can after detecting from the matched filter, just you can have the threshold device, and based on the threshold limit your decision either signal belongs to 1 or 0, you will get it, right? So for example, suppose the dotted line is representing the actual PT, that is masses, and PT plus NT, right? Here you can see the amplitude is changing because of the NT. So that is the the problem. So how can we detect the original masses? So that's a problem because of the noise. So here your output will be yt is equal to plus minus pt and plus nt, right? So noise is being added. So now question is that how we'll find out this matched filter, right? So matched filter, that is transfer function, that is our objective to find. Once we'll find the transfer function, then we'll multiply with the inputs and of course we'll get the output, right? So RT first we can write the the received signal, that is ST plus NT. This will be our received signal because ST your transmitted signal and your noise signal, right? So then output filter yt will be the what? Convolution in terms of the time domain, and in frequency domain simply the product of both, right? So here that convolution, and then we will try to maximize the SNR. So SNR, that is signal to noise ratio. So we'll find out the signal power and noise power, and then we'll take the SNR, right? And corresponding to that, what is the possible impulse response? That is the transfer function. So we will get it, and in the time domain also you can find. So these are the steps. So let's see here. So that is also called the optimum receiver filter for matched filter, right? So this is your SNR sigma square, that is equal to masses, that is P naught square divided by the sigma n square. So sigma, this one is showing the variance. So that is the in the noise power, that is why n is there. So first of all, what is our objective? Our objective to find the signal power, that is P naught square. So P naught is equal to nothing in the inverse Fourier transform F inverse and P of F and H of F. P of F is P of t is in the time domain, your pulse train, and P of F in frequency domain. Similarly, H of t, that is the impulse response in the time domain, H of F in the frequency domain. So just multiply both of them and take the inverse, you will get the P naught t, right? So you can convert it using the Fourier transform, basic Fourier transform function formula, like multiply by to the power j omega t in order to convert back into the time domain, right? This is the basic properties of Fourier transform, you can visit, right? And further, once if we'll get the P naught t, then our objective is to get the S and R, that is the noise ratio, so right? So noise ratio again here, and convolution of noise and the filter, right? The h of t minus t. So further you will get the noise. So once we'll get the power, that is the signal power and noise power, then we can put both and we'll get the ratio here. So ratio now we will got, but using the Cauchy inequality, it must be less than this number, this quantity, and we will target to get the maximum value of this. So how it should be maximized? In order to maximize your SNR, your h of f must be equal to this value, right? So that is why h of f, that is called the optimum received matched filter. So now if you will see here, what is this, like h of f? H of f is nothing, this is the k constant only. P of minus of f. P of f minus of f means your pulse train only in the frequency domain, and exponential of minus j omega, right? So and divided by the noise power. So roughly you can say that the power, that is message power, and divided by the noise power. So this is your matched filter. This is the very important equation for matched filter. You should remember it. Now we will talk about the probability of error, that is P of E. So actually what is happening, whenever we are sending the some information like pulse, that is 1 or 0, that is digital pulses, we may lose the information. So what is the chances, what is the probability that you will lose the information? So let's find out the probability of error. So suppose two signals like S1t and S2t as there, and so first we'll calculate the total energy for E1, E2, and then we'll compute the distance, and further you can find out the SNR d square by 2n. So once we'll get the SNR, then it is very easy to get the the probability of error after finding the SNR. How? Directly you can write probability of error is equal to Q, that is a one function, and then a square root of SNR. So if you know the SNR, put the value here, and that will be the probability of error. That's all, right? So now question is that what is this Q? So Q is a special function, that is 1 over twice a square root of twice pi and integration of x to infinity to the power minus t square by t into dt, to the power minus u square by 2 or du, whatever you are mentioning, right? So this is the function. So let's find out the your probability of error. So h of t, again you are in the time domain, p of t naught minus t naught, and similarly in the frequency domain, your h of f equal to p of minus f exponential of minus j. So probability of error is nothing. This a small equation you can remember, that is q of sigma max. Sigma is nothing, your SNR, that is signal to noise ratio, right? So given the matched filter under wide Gaussian noise, the matched filter receiver leads to rho max as well as the minimum BER, right? So if SNR is high, of course your probability of error will be minimum, right? So that will be the Q into a square root of twice EP divided by M. So this is the SNR for your case, right? In case of AWGN. So here is the bit error rate versus SNR graph for different cases. So for BPSK, right, you can check SNR is this, and like you can check it. So now we will talk about the binary signaling. So like what is the problem here? So we will like see here, if we are yt, that is equal to pt plus n of t. Pt is suppose the data transmitted for one symbol 1, and qt is representing the data symbol for 0. So problem is that like whenever we are sending pt and qt, there is some, the portion where both of the the data will overlap. So this is called the inter-symbol interference, right? So like because of this, the overlapping here, now the chances is that we may lose the information. So this is the another challenge here. So how can we find the probability of error here? So in case of the white Gaussian noise, first we have to find out the the SNR, and then further we can find out the probability of error in this binary cases, right? So here for the first time, first find out this is your beta max square, that is the twice by n, and infinite minus infinity to infinity, integrate it over in order to find the SNR. So here is your SNR, right? So final value. Now after finding this SNR value, you can put it here, that is probability of is equal to q of beta max by twice. So finally this is the probability of error for your binary signals, right? So like here p is denoting the error probability, and in binary case this error probability is the bit error probability or bit error rate, right? So and will be denoted by the pb. So this is the one of the standard equations that you have to remember. So b is representing only binary and p is the probability, and q is the function already we discussed in our last slide. Okay, now we'll talk about the inter-symbol interference. So already we have introduced here. Now see, suppose if we want to send the some information 1 and 0 and then again 1. So this is the very ideal case scenario, but here if you will see, like instead of 1, sometime you like it's going 0, and here it's continued to pass the 1, and here in this case also like we want to send 0, but it's not like 0, it's near to 1. So these are the regions where exactly the data is getting confused whether should I send 1 or 0. So overlapping regions, actually here both will overlap, 1 and 0 both. So that reason is called the inter-symbol interference only. So in digital communication, ISI, inter-symbol interference, is a form of distortion where one pulse or symbol spreads out and interfaces with adjacent symbol in the same signal. This makes it difficult for the receiver to distinguish between 1 and 0, leading to a higher probability of error, right? So it must not overlap. Now question is that how can we prevent to overlap? So and how we'll know that exactly whether is it overlapping or not? So there is a special criteria, that is Nyquist first criteria for zero ISI, right? So here Nyquist achieves zero ISI by choosing a pulse shape that has a non-zero amplitude at its center, and zero amplitude at t is equal to plus minus n tb. Here n will be equal to 1 2 3 4 and that, right? So pt is nothing, pt is equal to 1 at t is equal to 0, and pt equal to 0 for t is equal to at 1T, 2TB and 3TB, whatever. And TB is nothing 1 by R of B, right? So in frequency domain, in time domain, we are considering time. In time domain, we are considering the time period TB, and in frequency domain, like this is the 1 by RB, that is frequency, right? So here you can see this is the rectangular function, and corresponding to rectangular function, what will be the time domain function? That is your sync. So here multiple syncs are combining. So again, the whenever it's overlapping, since like it have the certain components, not it will go for longer time. So wherever it is overlapping, it of course it causes to the ISI, inter-symbol interference, right? So now transmission of RB bits per second requires a theoretical minimum bandwidth, that is RB by 2, in order to maintain the in order to reconstruct the signal properly. It would be nice if pulse satisfying Nyquist criteria had this minimum bandwidth, that is RB by 2, otherwise no option, right? So we have already solved this problem, like we have discussed in the Nyquist criteria in the PCM only, where we discussed why is it important, right? So sync function, why is this sync function? And these are your, the corresponding to the rectangular functions. If you will convert back in the inverse Fourier transform, you will get sync function. So the more Fourier transform of this pulse is nothing, P of f is equal to 1 by RB, pi of f by RB. So this is in the frequency domain corresponding to this, and this is in the time domain corresponding to this sync function, right? So both are representing the mathematical equation for sync function and for this. Okay, so here now some more details about the ISI, that is inter-symbol interference here. How to find out the exactly the the bit. So here we'll find out the amount of the roll factor also. So see first, like we'll find out the overlapping regions. So first we'll sum, that is P of f minus RB. RB is nothing, that is 1 by RB is equal to your T of B only, that is the RB is equal to 1 by TB. So RB is representing the frequency here, and TB is the time period for first one only, right? So TB, twice TB and thrice TB, it will continue in sync function if you will see. So let's add them the the powers. So here P of x plus 0.5 RB for first one, and the left side also, left half, that will be equal to the T of B, right? So right half and the left half, so we'll get the total T of B, and further if you calculate, you will get the value like P of half of RB is equal to 0.5 of P of 0. P of 0 is telling the the while you are transmitting the 0. So and so finally your R, that is the bandwidth in hertz, and the R is nothing, roll-off factor, that can be estimated by the ratio of the excess bandwidth divided by the theoretical minimum bandwidth, right? So that is equal to f of x divided by 0.5 RB. So R will be equal to twice of fx TB. In terms of the frequency, the theoretical minimum bandwidth is RB by 2, and the excess bandwidth is fx is equal to R, small r, and RB divided by 2. Therefore, the bandwidth of PF is how much? Bt is equal to RB by 2 for first sync function, and then into plus of R, RB by 2. So total it will be 1 plus R, that is a small r, roll factor, into RB divided by 2. So this is the total transmitted bandwidth for your signal, right? So here roll factor, like already we discussed, that is a small r is a roll factor, and is also expressed in terms of the percent. For example, PF is a Nyquist first criteria, which is a bandwidth that is the 50% higher than a theoretical minimum is a roll factor, that is R is equal to 0.4 0.5 here. Okay, so because R must be in between 0 to 1 only, the bandwidth of PF is restricted in the range of RB by 2 to RB hertz. The pulse PT can be generated as a unit impulse response of a filter with transfer function P of f, right? But because P of f equal to 0 over the frequency band, it violates the Paley-Wiener criteria and it therefore unrealizable. However, the vestigial role of characterize the gradual and it can be approximated by this filter, that is Pf equal to 1 if this if frequency is in the range of the the Rb by 2 minus of f naught. This for this reason, and if it PFF will be half, right? So this is your one only, and PFF will be half of 1 minus sin pi for this reason, and f minus r rb by 2 to divided by twice of max for less than f minus rbb rb whole square by 2 less than f of x. And finally it will be 0 if f is greater than here in this case, right? So rb by 2 plus ff. Okay, so here in time domain, this is in the frequency domain, same things, the PFF you can convert into the time domain, and this characteristic is also called as the raised cosine characteristic because it represents the cosine raised in the peak amplitude, right? This is in your cosine raised only. It is also known as the full cosine role of characteristic, and the same things you can convert back into the time domain, that is P of t equal to Rb and cos pi Rb naught Rbt divided by 1 minus 4 pi square t square sin pi Rbt, right? So this is, and now we'll talk about the something about the eye diagram. So this is also a very important tool, and so you should know eye diagram is a pattern critical diagnostic tool in digital communication used to evaluate the quality of a signal and the impact of inter-symbol interference. It created by overlapping successive symbol period of a digital signal or an oscilloscope, right? As for example, here you can see here this is transmitting the 1 and this one is transmitting the 0. So now if we will see the the symbol 1 and 0, then the combination of both looks like eye, right? So this person, so that is why this is called the eye diagram. So once if we'll transmit the numerous numbers of the 1 and 0, then it will creates the almost eye. Now different parameters are there. First, if eye opening height represents the noise margin, right? So if it is very high, it will have the good noise margin. A wide spectral opening means the signal resistant to noise. If the eye is nearly closed, means this is very less, 1 and 0, it means it's a very noisy signal. So these are the information. And eye width, that is eye width, it will tell you the this indicates the time interval which the signal can be sampled without error. And jitter is there, the time interval here. So jitter width, that is the width of the crossing, so the horizontal thickness at the point where the signal lines intersect, right? 1 and 0, wherever it will intersect, and the thickness, that is the jitter width. It shows the timing uncertainty or fluctuation in the signal. And zero crossing distortion, that is this indicates the timing jitter and synchronization problem. And slope of the eye, so slope of the eye, that will represent the determines the sensitivity of the timing error. So slipper slope means that a small shift in the sampling time will lead to the larger decrease in the signal to noise ratio. So like here the overall summary is the, this is your eye diagram where it representing the 0 level and this is the 1 level. So it will take some time to go to the 0 to 1, and it will take some time to come 1 to 0, and if you'll combine the multiple signals, then automatically this will form the eye type of the diagram. And definitely ideally it should be like okay, it should immediately go to 1 as and then come to 0, and it should come 0 to 1. But instead of the rectangular function, this is making something like eye diagram. So if it is opening, your eye opening height is good enough, then noise is less, and if it is closer means noise is very high. So these are the summary here. So here is the some more details. So maximum opening height, so the eye opening amount of the at the sampling, and decision instant indicates the amount of the noise the detector can tolerate without making an error. The quantity is known as the noise margin, right? So the instant of the maximum eye opening indicate the optimum sampling or decision making instant. So you can go through that for more details. Here is the summary only. So sampling and decision instant is here. So another sample normal eye, like it is clear from the comparison of these two diagrams have a simple horizontal circular shift relationship. By observing the maximum eye opening, we can see that the baseband signal has zero or no ISI, right? And if it is closer means, of course, if it is closer means like this will the height will come like that in that case your noise will be very high. So because Nyquist first criteria place no requirement on the zero crossing of the pulse, the eye diagram indicates that the time jitter would be likely. Okay, so here is the summary for your eye diagram, and so check all this. Like already we have discussed, the noise margin should be high, and if it is the closer, near to closer means very high noise here. Okay, that's all in this session. Thank you to join. If you have any doubts, please drop your comments. Thank you.